Picture this, a universe so young, so unimaginably hot and dense, that the very building blocks of everything we know and see today were just beginning to take shape. What if I told you that the very first elements, those tiny seeds of hydrogen, helium, and a sprinkle of lithium hold secrets that could rewrite our understanding of the cosmos? How did these simplest of elements lay the foundation for stars, galaxies, and even life itself? And what if their creation wasn't just a simple cosmic recipe, but a puzzle so intricate that it still baffles scientists today? As we dive into the mysteries of the universe's first light elements, we'll uncover theories that stretch the limits of our imagination, from the echoes of the Big Bang to the whispers of dark matter. So stay with us, because by the end of this video, you'll see the universe in a way you never have before, where even the smallest atoms tell the grandest stories. Let's begin our journey into the origins of everything. Now, let's take our first step into unraveling this cosmic mystery with the Primordial Nucleosynthesis model. Think of the early universe as an immense, seething cauldron of energy, where temperatures were so extreme that atoms couldn't even exist yet. In the first few minutes after the Big Bang, the universe was a chaotic soup of protons, neutrons, and other subatomic particles, all zipping around at unimaginable speeds. But as the universe expanded, it began to cool, and that's when something extraordinary happened. Protons and neutrons started to combine, forming the simplest atomic nuclei. Hydrogen, the most basic element, was the first to emerge with its single proton. Helium soon followed as pairs of protons and neutrons came together. And in this cosmic ballet, even trace amounts of lithium were formed, though in much smaller quantities. This process, known as nucleosynthesis, lasted for just a few minutes but set the stage for everything that came after. It's fascinating to think that the hydrogen and helium created in those brief moments became the fuel for the first stars, the building blocks of galaxies, and ultimately the foundation of life itself. This model isn't just a theory, it's supported by the observed abundances of these elements in the universe today, matching predictions with remarkable precision. So, as we peel back the layers of this theory, we're not just exploring the birth of elements, we're uncovering the very blueprint of the cosmos. Now turning to another intriguing perspective, let's explore the inhomogeneous Big Bang Theory. While the Primordial Nucleosynthesis model paints a picture of a smooth, uniform early universe, this alternative idea challenges that notion. What if the cosmos wasn't perfectly even in those first moments? What if instead it was a patchwork of dense and sparse regions, like ripples on the surface of a pond? This theory suggests that these irregularities could have profoundly influenced the formation of the first light elements. In denser areas, the conditions might have been ripe for rapid nucleosynthesis, producing more hydrogen, helium, and lithium than in less dense regions. These variations could explain some of the subtle differences we observe in the distribution of elements across the universe today. It's a fascinating thought that the universe's earliest moments might have been as chaotic and varied as the galaxies we see now. While this theory is still speculative, it opens up new avenues for understanding how the first elements came to be and why they're distributed the way they are. Next, we'll delve into how dark matter might have played a role in this cosmic dance of element formation. Now shifting our focus to one of the most mysterious players in the cosmos, let's consider the role of dark matter in the formation of the first light elements. While we can't see dark matter directly, its gravitational effects are undeniable, shaping galaxies and influencing the structure of the universe itself. But could it have also played a part in the creation of hydrogen, helium, and lithium in the early universe? Some theories suggest that dark matter particles might have interacted with ordinary matter in ways we don't yet fully understand. These interactions could have altered the temperatures or densities in certain regions of the early universe, creating pockets where nucleosynthesis occurred more efficiently. Imagine dark matter as a hidden hand, subtly guiding the process of element formation behind the scenes. While this idea remains speculative, it offers a tantalizing possibility that dark matter wasn't just a passive observer in the early universe, but an active participant in shaping the first chemistry of the cosmos. As we continue to unravel the secrets of dark matter, we may uncover clues about its role in the birth of the very elements that make up everything we see today. Next, we'll explore another fascinating phase of the universe's history, the Quark-Gluon Plasma Era and its transition into the elements we know. Now turning to a pivotal moment in the universe's infancy, let's dive into the Quark-Gluon Plasma phase. Picture the universe just moments after the Big Bang, a seething, unimaginably hot soup of fundamental particles. During this time, the universe was too energetic for protons and neutrons to form. Instead, it was dominated by quarks and gluons, the building blocks of matter, freely swirling in a state of plasma. This quark-gluon plasma was the universe's first soup, a chaotic yet crucial stage in its evolution. As the universe expanded and cooled, this plasma began to condense, allowing quarks and gluons to combine and form protons and neutrons. This marked the beginning of nucleosynthesis, the process that created the first light elements like hydrogen and helium. The transition from quark-gluon plasma to stable matter was a delicate dance of energy and cooling, setting the stage for the universe's chemistry. Without this phase, the elements essential for stars, planets, and life itself might never have formed. The study of quark-gluon plasma not only sheds light on the universe's earliest moments, but also helps us understand the fundamental nature of matter itself. Next, we'll explore how neutron capture, a process typically associated with stars, might have played a surprising role in the formation of the first light elements. Now shifting our focus to a fascinating twist in the cosmic story, let's explore the neutron capture process. While this mechanism is often linked to the later stages of stellar nucleosynthesis, it might have also played a surprising role in the formation of the universe's first light elements. Neutron capture occurs when an atomic nucleus absorbs a neutron, increasing its mass and potentially transforming into a different element. In the early universe, this process could have been triggered by the presence of free neutrons left over from the quark-gluon plasma phase. As protons and neutrons began to stabilize, some neutrons might have been captured by lighter nuclei, such as hydrogen or helium, leading to the creation of slightly heavier elements like deuterium or lithium. This process, though more common in stars, could have contributed to the early chemical makeup of the universe during its most chaotic and energetic moments. The idea challenges our understanding of element formation, suggesting that even the first elements might have had a more complex origin than previously thought. By examining neutron capture in this context, scientists gain new insights into how the building blocks of the cosmos came to be. Next, we'll delve into how quantum fluctuations in the early universe might have shaped the distribution of these light elements, adding another layer of intrigue to this cosmic puzzle. Now considering the subtle dance of the cosmos at its earliest moments, let's turn our attention to the influence of quantum fluctuations. These tiny, unpredictable changes in energy levels are a fundamental aspect of quantum mechanics, and they might have played a surprising role in shaping the universe's first light elements. In the first fractions of a second after the Big Bang, the universe was a seething, chaotic environment where quantum fluctuations could cause slight variations in density. These variations, though incredibly small, could have had a ripple effect, creating pockets where certain elements formed more readily than others. For example, regions with slightly higher densities might have seen a greater concentration of hydrogen and helium, while areas with lower densities could have produced trace amounts of lithium or deuterium. Over time, these fluctuations could have influenced the overall distribution of light elements across the cosmos, essentially planting the seeds for the structure of the universe we see today. This idea ties the quantum world to the cosmic scale, suggesting that the tiniest fluctuations in the early universe had far-reaching consequences for the chemistry of the cosmos. As we ponder this connection, it's fascinating to think that the very fabric of the universe might owe its complexity to these microscopic quirks. Next, we'll uncover the mystery of baryon asymmetry and how it shaped the dominance of matter over antimatter in the early universe. Now shifting our focus to one of the most puzzling questions in cosmology, we encounter the baryon asymmetry problem. This mystery asks why our universe is filled with matter, while antimatter seems to have all but disappeared. According to the laws of physics, the Big Bang should have created equal amounts of matter and antimatter. Yet when these two meet, they annihilate each other, leaving behind pure energy. So, if there had been perfect symmetry, the universe as we know it would not exist. The fact that matter dominates suggests that at some point, a tiny but crucial imbalance occurred. This imbalance is believed to have taken place in the first moments after the Big Bang, during a process called baryogenesis. Here, a slight excess of matter over antimatter emerged, perhaps due to conditions that violated certain symmetries in particle physics. This asymmetry had a profound impact on the formation of the first light elements. Without it, hydrogen and helium, the building blocks of stars and galaxies, might never have formed in the quantities we observe today. The excess matter allowed nucleosynthesis to proceed, creating the elements that would later shape the cosmos. This delicate imbalance raises questions about the fundamental nature of the universe and the conditions that made our existence possible. As we explore this mystery further, it's worth considering how such a seemingly small deviation could have set the stage for everything we see around us. Next, we'll examine how the cosmic microwave background provides clues about the abundance of these early elements. With the cosmic microwave background now in focus, let's uncover how this ancient afterglow of the Big Bang holds vital clues about the universe's first light elements. The CMB is essentially a snapshot of the universe when it was just 380,000 years old, capturing the moment when photons first traveled freely through space. Embedded within this faint radiation are patterns and fluctuations that reveal crucial information about the early universe's composition. One of the most compelling pieces of evidence found in the CMB is the ratio of hydrogen to helium. Measurements of this ratio align almost perfectly with predictions made by the theory of primordial nucleosynthesis, the process that formed the first elements. This agreement between observation and theory not only supports our understanding of how hydrogen and helium came to dominate the early universe, but also reinforces the idea that the conditions during the Big Bang were just right for these elements to form. Additionally, the CMB's temperature fluctuations provide insights into the density of matter in the early universe, which in turn influenced how elements were distributed. These tiny variations in temperature map out regions where matter was slightly more or less dense, offering a glimpse into how the first structures in the cosmos began to take shape. By studying the CMB, scientists can piece together a detailed picture of the universe's infancy, shedding light on how the first light elements were created and how they set the stage for the complex structures we see today. As we move forward, the cosmic microwave background remains one of our most powerful tools for unraveling the mysteries of the universe's earliest moments. As we venture deeper into the mysteries of the universe's first light elements, let's turn our attention to one of the most elusive players in the cosmic drama, neutrinos. Often referred to as ghost particles, neutrinos are nearly massless, electrically neutral particles that interact so weakly with matter that they can pass through entire planets without leaving a trace. Yet, despite their ghostly nature, neutrinos might have had a profound influence on the chemistry of the early universe. In the moments following the Big Bang, the universe was a seething cauldron of energy and particles, including vast numbers of neutrinos. These particles, though barely interacting with others, could have subtly altered the balance of matter and energy. Some theories suggest that neutrinos played a key role in the synthesis of helium, the second most abundant element in the universe. By influencing the rate at which protons and neutrons combined, neutrinos might have helped determine the final amounts of hydrogen and helium that filled the cosmos. Additionally, the presence of neutrinos could have affected the conditions under which other light elements formed. Their interactions, though faint, might have created slight deviations in temperature and density, shaping the distribution of elements in ways we are only beginning to understand. While neutrinos remain mysterious, their potential role in the universe's earliest chemistry opens up fascinating possibilities. As we continue to explore these ghostly particles, we may uncover even more about how they helped shape the cosmos we see today. Now shifting our focus to a pivotal moment in the universe's infancy, we arrive at the Lepton era, a time when leptons ruled the cosmos. These lightweight particles, which include electrons and neutrinos, were the dominant players in this early stage, shaping the conditions for the formation of the first light elements. During the Lepton era, the universe was still incredibly hot and dense, but it had cooled enough for electrons, positrons, and neutrinos to take center stage. This era followed the Quark-Gluon Plasma phase, marking a critical transition in the universe's evolution. At this time, particles and antiparticles constantly annihilated each other, releasing energy and keeping the cosmos in a state of dynamic equilibrium. However, as the universe continued to expand and cool, the balance shifted. Electrons and positrons began to annihilate less frequently, leaving behind a surplus of electrons. This created a stable environment where protons and neutrons could start combining to form the nuclei of the first elements. Neutrinos, though still playing their ghostly role, also contributed to this process by influencing the interactions between particles. The Lepton era set the stage for nucleosynthesis, the process that would eventually give rise to hydrogen, helium, and trace amounts of lithium. Without this period of leptonic dominance, the universe might not have developed the building blocks necessary for stars, galaxies, and ultimately, life. By understanding the Lepton era, we gain deeper insights into how the universe's early chemistry unfolded, paving the way for the rich tapestry of elements we see today. This era reminds us that even the smallest particles played a monumental role in shaping the cosmos. Now turning to one of the most fundamental yet overlooked aspects of the early universe, we encounter the photon-baryon ratio. This ratio, which refers to the number of photons compared to baryons, played a crucial role in determining how the first light elements came to be. In the early moments of the cosmos, photons outnumbered baryons by an astonishing factor of around 1 billion to 1. This overwhelming abundance of photons created a hot, dense environment where particles were constantly colliding and interacting. These interactions were critical for the formation of hydrogen and helium, as photons provided the energy needed to facilitate reactions between protons and neutrons. However, as the universe expanded and cooled, the photon-baryon ratio began to influence the process in a different way. The high number of photons acted as a sort of pressure, preventing protons and neutrons from combining too quickly. This delay allowed for the precise conditions necessary for nucleosynthesis to occur efficiently. Without this carefully balanced ratio, the universe might have ended up with a vastly different chemical makeup, potentially disrupting the formation of stars and galaxies. The photon-baryon ratio not only highlights the delicate balance of the early universe, but also underscores how even the tiniest details can have profound consequences. It's a reminder that the cosmos operates on a scale of precision that continues to amaze us as we unravel its mysteries. As we step into the next chapter of our cosmic journey, let's explore the remarkable role of cosmic inflation in shaping the universe's first light elements. Cosmic inflation refers to the brief but extraordinary period immediately after the Big Bang when the universe expanded exponentially, stretching far beyond what we can observe today. This rapid expansion had a profound impact on the conditions necessary for the formation of hydrogen, helium, and trace elements. During inflation, the universe cooled dramatically, allowing energy to condense into matter. This cooling set the stage for particles to interact and combine, forming the building blocks of the first elements. However, inflation also smoothed out the universe, creating a remarkably uniform distribution of matter and energy. This uniformity ensured that the processes of nucleosynthesis, which formed hydrogen and helium, occurred consistently across the cosmos. Without this smoothing effect, the universe might have been far more chaotic, with pockets of extreme density and emptiness, making it difficult for light elements to form in abundance. Additionally, inflation amplified tiny quantum fluctuations, seeding the structures we see today, like galaxies and galaxy clusters. These fluctuations also influenced the distribution of light elements, ensuring they weren't spread too thin or clustered too densely. Cosmic inflation, therefore, wasn't just a dramatic event in the universe's history. It was a cornerstone that shaped the very chemistry of the cosmos. By understanding this phase, we gain deeper insights into how the delicate balance of the early universe allowed the first elements to emerge, paving the way for everything that followed. Now shifting our focus to the deuterium bottleneck, we uncover one of the most fascinating and pivotal moments in the formation of the universe's first light elements. Deuterium, also known as heavy hydrogen, is an isotope of hydrogen that contains one proton and one neutron. Its creation and survival in the early universe were crucial for the synthesis of heavier elements. During the first few minutes after the Big Bang, temperatures were incredibly high, allowing protons and neutrons to collide and form deuterium. However, deuterium is relatively fragile, and at such high temperatures it could easily break apart before forming more stable nuclei. This created a bottleneck, a delay in the production of helium and other elements until the universe cooled enough for deuterium to survive. As the temperature dropped, deuterium could finally remain intact, enabling the next stage of nucleosynthesis where deuterium nuclei combine to form helium. Without this bottleneck, the delicate balance of element formation would have been disrupted, potentially leading to a very different universe. Interestingly, the amount of deuterium observed today serves as a cosmic thermometer, providing clues about the density of matter in the early universe. By studying this bottleneck, scientists can better understand the conditions that allowed the first elements to emerge and how those elements laid the foundation for the cosmos we see today. Now delving into the mystery of helium's abundance, we uncover one of the most compelling cosmic puzzles. Helium is the second most abundant element in the universe, trailing only hydrogen, yet its origins and prevalence have long intrigued scientists. During the universe's infancy, helium was forged through a process called Big Bang Nucleosynthesis. In the first few minutes after the Big Bang, the intense heat and pressure allowed protons and neutrons to collide, forming deuterium, which then combined to create helium. This rapid synthesis left behind a significant amount of helium, accounting for about 25% of the universe's elemental composition. However, the abundance of helium raises questions. Why is there so much of it? One key factor lies in the stability of helium's nucleus. Helium, specifically its isotope helium-4, is incredibly stable, making it resistant to breaking apart. This stability ensured that once formed, helium persisted as the universe expanded and cooled. Another theory suggests that the helium abundance was influenced by the ratio of protons to neutrons in the early universe. When temperatures were high enough for nuclear reactions, neutrons combined with protons to form helium, leaving behind a surplus that remains detectable today. Additionally, observations of the cosmic microwave background and the spectra of ancient stars provide evidence for helium's primordial origins. These findings support the idea that helium's abundance is a direct consequence of the early universe's conditions. Yet, some scientists speculate that stellar nucleosynthesis, the process by which stars fuse hydrogen into helium, may have also contributed to its prevalence. The interplay between these processes paints a complex picture of helium's formation and distribution. Understanding helium's abundance not only sheds light on the early universe, but also helps us grasp the fundamental processes that shape the cosmos. As we continue to explore this mystery, the answers may reveal deeper insights into the universe's first moments and the forces that govern it. Now shifting our focus to another cosmic enigma, we encounter the lithium problem, a puzzling discrepancy that has baffled scientists for decades. According to the predictions of Big Bang nucleosynthesis, the early universe should have produced a specific amount of lithium, particularly its isotope lithium-7. However, observations of ancient stars and other cosmic sources reveal significantly less lithium than expected. This inconsistency has sparked a wide range of theories attempting to explain the missing lithium. One prominent idea suggests that lithium might have been destroyed or altered in the interiors of early stars. As these stars burned hydrogen and helium, their intense heat could have caused lithium to break down, reducing its abundance over time. Another theory points to the possibility of unknown physical processes during the early universe that might have suppressed lithium formation. Some researchers speculate that cosmic rays, high-energy particles traveling through space, could have interacted with lithium nuclei, transforming them into other elements. Additionally, variations in the density and temperature of the early universe might have played a role, creating conditions that hindered lithium production. Some even propose that our understanding of nuclear physics might be incomplete, requiring new models to account for the observed lithium levels. Despite these efforts, the lithium problem remains unresolved, highlighting the complexities of the universe's earliest moments. Solving this mystery could not only refine our understanding of Big Bang nucleosynthesis, but also provide deeper insights into the fundamental forces that shape the cosmos. As we continue to explore this intriguing puzzle, the answers may lie hidden in the stars, waiting to be uncovered. Now stepping into the realm of the earliest cosmic structures, we explore how the first generation of stars, often called population 3 stars, shaped the universe's elemental landscape. These ancient stars, born from the primordial soup of hydrogen and helium, were unlike anything we see today. They were massive, short-lived, and incredibly hot, burning through their fuel at an astonishing rate. As they reached the end of their lives, they exploded in powerful supernova, scattering their contents across the cosmos. These explosions were not just dramatic cosmic events, but also cosmic forges, creating heavier elements like carbon, oxygen, and nitrogen, which were then seeded into the surrounding space. This process, known as stellar nucleosynthesis, marked the beginning of chemical complexity in the universe. These newly formed elements became the building blocks for future stars, planets, and even life itself. But the impact of these early stars went beyond just creating heavier elements. Their intense radiation also played a crucial role in reionizing the universe, transforming it from a dark, neutral state to the bright, ionized expanse we observe today. This reionization process helped shape the large-scale structure of the universe, influencing how galaxies formed and evolved over time. Additionally, the remnants of these early stars, including black holes and neutron stars, became the seeds for the cosmic structures we see today. By studying these ancient stars, astronomers can trace the origins of the elements that make up our world and better understand the intricate processes that shaped the universe in its infancy. The legacy of these first stars is written in the stars and galaxies that surround us, a testament to their profound impact on the cosmic story. Now shifting our gaze to the invisible forces that shaped the early cosmos, let's explore the role of cosmic rays in the formation of the universe's first light elements. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. These particles, often protons or atomic nuclei, originate from various sources, including supernova and other powerful astrophysical events. In the early universe, cosmic rays may have played a surprisingly significant role in the synthesis of light elements. As these particles collided with nuclei in the primordial environment, they could have triggered nuclear reactions that produced elements like hydrogen, helium, and even traces of lithium. This process, known as spallation, involves cosmic rays breaking apart heavier nuclei into lighter ones, effectively contributing to the cosmic abundance of these elements. Additionally, cosmic rays could have influenced the temperature and density of the early universe, creating conditions that favored the formation of certain elements over others. While this theory is still speculative, it offers a fascinating perspective on how these high-energy particles might have shaped the elemental makeup of the cosmos. By studying cosmic rays today, scientists can gain insights into the conditions of the early universe and the processes that gave rise to the building blocks of matter. The interplay between cosmic rays and the formation of light elements remains an area of active research, highlighting the complexity and interconnectedness of cosmic forces. As we continue to unravel these mysteries, we're reminded that even the most unseen and subtle phenomena can have profound effects on the universe's evolution. Now shifting our focus to another intriguing possibility, let's explore the idea that primordial black holes could have influenced the creation of the universe's first light elements. Primordial black holes, if they exist, are thought to have formed in the very early universe, potentially within the first second after the Big Bang. These black holes, unlike the ones formed from collapsing stars, would have been incredibly small yet incredibly dense. Some scientists speculate that these tiny black holes might have played a role in the synthesis of elements by creating unique conditions in the early cosmos. As these black holes interacted with their surroundings, they could have heated nearby matter, triggering nuclear reactions that produced hydrogen and helium. Additionally, their gravitational pull might have concentrated matter in certain regions, enhancing the likelihood of element formation. Another fascinating idea is that primordial black holes could have acted as catalysts for the formation of heavier elements, such as lithium, by altering the density and temperature of the early universe. While this theory remains highly speculative and lacks direct observational evidence, it opens up exciting avenues for understanding the universe's elemental origins. If primordial black holes did exist, their influence could have been subtle yet significant, shaping the distribution and abundance of light elements in ways we are only beginning to imagine. Exploring this theory further could provide deeper insights into the mysterious forces that shaped the cosmos in its infancy. As we continue to investigate, the potential role of primordial black holes adds another layer of complexity to the story of the universe's first chemistry. Now turning to another fascinating aspect of the early universe, let's delve into the potential role of magnetic fields in shaping the first light elements. In the moments following the Big Bang, the universe was not only a hot, dense soup of particles, but also a place where magnetic fields could have emerged. These fields, though initially weak, might have had a surprisingly significant influence on how elements like hydrogen and helium formed and spread across the cosmos. One idea suggests that magnetic fields could have affected the motion of charged particles, such as protons and electrons, in the early universe. By directing the flow of these particles, magnetic fields might have created regions where conditions were more favorable for nuclear reactions to occur. This could have led to localized increases in the production of light elements, resulting in patchy distributions rather than a perfectly uniform spread. Another intriguing possibility is that magnetic fields played a role in shaping the structure of the universe on larger scales. As the universe expanded, these fields might have guided the formation of early cosmic structures, such as filaments and voids, which in turn influenced where and how elements were distributed. This interplay between magnetic fields and the evolving cosmos could have left a subtle but lasting imprint on the abundance of light elements we observe today. While the evidence for these early magnetic fields remains indirect, their potential impact is a compelling area of study. Understanding how they might have influenced the synthesis and distribution of the first elements could help us piece together a more complete picture of the universe's origins. As we continue to explore this theory, the role of magnetic fields adds yet another layer of depth to the intricate story of the cosmos's first chemistry. As we venture into the next layer of this cosmic puzzle, let's consider the mysterious world of exotic particles and their potential role in the formation of the first light elements. Beyond the standard model of particle physics, there exists a realm of particles that could have played a part in shaping the early universe's chemistry. These exotic particles, often theoretical and undetected, might hold the key to understanding some of the lingering mysteries of element formation. One compelling idea is that exotic particles, such as actions or sterile neutrinos, could have interacted with ordinary matter in ways that influenced the synthesis of hydrogen and helium. These interactions might have altered the conditions under which nuclear reactions occurred, leading to variations in the abundance of light elements. For example, if exotic particles decayed or annihilated in the early universe, they could have released energy that affected the temperature and density of the primordial plasma, creating pockets where element formation unfolded differently. Another intriguing possibility is that exotic particles contributed to the asymmetry between matter and antimatter, a phenomenon crucial for the existence of the universe as we know it. If these particles were involved in processes that tipped the balance in favor of matter, they could have indirectly influenced the creation of the first elements. This connection between exotic particles and the matter-antimatter imbalance opens up a fascinating avenue for exploring the roots of the universe's chemistry. While the existence of these particles remains speculative, their potential impact on early element formation is a captivating area of research. By studying their hypothetical effects, scientists hope to uncover new insights into the universe's origins and the processes that shaped its fundamental building blocks. The role of exotic particles adds yet another intriguing layer to the intricate tapestry of the cosmos's first moments. As the narrative expands beyond our own universe, let's delve into the intriguing possibility of the multiverse and its implications for the formation of the first light elements. The multiverse theory suggests that our universe might be just one of many, each with its own unique physical laws and conditions. This raises a fascinating question. Could the abundance of light elements like hydrogen and helium vary across these different universes? In some universes, the fundamental constants, such as the strength of nuclear forces or the rate of cosmic expansion, might differ significantly from those in our own. These variations could lead to entirely different outcomes in the synthesis of light elements. For instance, a universe with stronger nuclear forces might produce more helium during the primordial nucleosynthesis phase, while another with weaker forces might result in less. The multiverse concept also introduces the idea that the balance between matter and antimatter, which played a crucial role in shaping our universe's chemistry, might be entirely different elsewhere. In some universes, antimatter could dominate, leading to a very different set of elements or perhaps even preventing the formation of stable matter altogether. While the multiverse remains a speculative idea, it opens up a vast landscape of possibilities for understanding the origins of light elements. If other universes exist, each could serve as a natural laboratory, offering insights into how slight changes in physical laws can dramatically alter the cosmic recipe. Exploring the multiverse's potential impact on element formation not only deepens our understanding of the universe's beginnings, but also challenges us to think beyond the boundaries of our own cosmic neighborhood. This theory invites us to imagine a cosmos far richer and more diverse than we've ever conceived, where the first light elements might tell entirely different stories in each unique universe. Now stepping into the realm of theoretical physics, let's explore how string theory might shed light on the formation of the universe's first elements. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings oscillate at different frequencies, giving rise to the various particles and forces we observe. At the heart of string theory is the idea that these vibrations occur in higher dimensions beyond the three spatial dimensions and one time dimension we experience. This framework could help explain phenomena that remain puzzling in the standard model of particle physics, such as the precise conditions during the universe's earliest moments. When it comes to the formation of light elements, string theory suggests that the interactions between these vibrating strings could have influenced the early universe's chemistry. For instance, the specific frequencies of string vibrations might have determined the strengths of fundamental forces like gravity and electromagnetism, which in turn shaped the synthesis of hydrogen, helium, and lithium. Moreover, string theory introduces the concept of brane multidimensional objects that could have existed in the early universe. Collisions or interactions between these branes might have triggered events like the Big Bang, setting the stage for the formation of the first elements. Understanding these processes could provide new insights into why the abundance of light elements in our universe is what it is today. While string theory is still a work in progress and remains unproven, it offers a fascinating perspective on the origins of the universe's first light elements. By bridging the gap between quantum mechanics and general relativity, it challenges us to rethink our understanding of the cosmos and the fundamental forces that shaped it. As we continue to unravel the mysteries of string theory, we may find that it holds the key to unlocking one of the universe's oldest secrets, how the first elements came to be. This groundbreaking theory invites us to imagine a universe where the tiniest vibrations of strings could have cosmic consequences, forever altering our understanding of the cosmos. Now shifting our perspective, let's explore the holographic principle and its intriguing connection to the universe's first light elements. This principle suggests that all the information contained within a volume of space can be represented as a hologram, a two-dimensional surface at the boundary of that space. At first glance, it might sound like science fiction, but this idea has profound implications for our understanding of the early universe. The holographic principle stems from the study of black holes and quantum gravity, where it was discovered that the entropy, or the amount of information, of a black hole is proportional to the surface area of its event horizon, not its volume. This led to the radical idea that the universe itself might operate like a hologram, with all its complexity encoded on a boundary surface. So, how does this relate to the formation of the first light elements? If the holographic principle holds true, the early universe's chemistry could have been fundamentally shaped by information encoded on its two-dimensional boundary. The interactions and processes that led to the synthesis of hydrogen, helium, and lithium might have been governed by patterns and rules embedded in this cosmic hologram. This perspective opens up new ways to think about the conditions of the early universe. For example, the specific abundances of light elements we observe today could be seen as a reflection of the information stored on the universe's holographic boundary. It's a fascinating concept that challenges our traditional view of three-dimensional space and time, suggesting that the universe's first chemistry might have been a projection of deeper, underlying principles. While the holographic principle remains a theoretical framework, it offers a fresh lens through which to examine the mysteries of the early universe. By reimagining the cosmos as a hologram, we might uncover new clues about how the first elements came to be, bridging the gap between quantum mechanics and cosmology in ways we're only beginning to understand. As we continue to explore this groundbreaking idea, we're reminded that the universe's secrets often lie in the most unexpected places, even on the surface of a two-dimensional boundary. Now shifting our focus to another groundbreaking idea, let's delve into the concept of supersymmetry and its potential role in shaping the universe's first light elements. Supersymmetry, often referred to as SUSY, is a theoretical framework that suggests every known particle has a yet-to-be-discovered superpartner. While this idea was originally proposed to address puzzles in particle physics, it also has fascinating implications for the early universe. If supersymmetry exists, it would mean that the early universe was teeming with these superparticles, each with unique properties and behaviors. These particles could have influenced the conditions under which the first light elements formed. For instance, the presence of superparticles might have altered the rate of reactions during the Big Bang nucleosynthesis, the process responsible for creating hydrogen, helium, and trace amounts of lithium. One intriguing possibility is that supersymmetry could explain some of the discrepancies in our current understanding of element formation. For example, the observed abundance of lithium in the universe is much lower than what our models predict. Supersymmetry might offer a solution to this so-called lithium problem by introducing new interactions or decay processes involving superparticles. Furthermore, supersymmetry could provide a deeper understanding of the universe's initial conditions. The superparticles, with their distinct masses and interactions, might have played a role in determining the balance between matter and antimatter, ultimately influencing the distribution of the first elements. While supersymmetry remains unproven, its potential impact on the early universe's chemistry is a compelling area of study. As we continue to explore this theory, we're reminded that the universe's earliest moments might have been shaped by particles and forces we're still striving to understand. Supersymmetry offers a tantalizing glimpse into a hidden layer of reality, one that could hold the key to unlocking the mysteries of the universe's first light elements. Now turning to the intersection of two of the most profound areas of physics, let's explore how quantum gravity might reshape our understanding of the universe's first light elements. Quantum gravity seeks to merge the principles of quantum mechanics, which govern the smallest particles, with general relativity, which describes the behavior of massive objects and space-time itself. While unifying these two frameworks remains one of science's greatest challenges, it could also provide groundbreaking insights into the early universe. In the moments following the Big Bang, the universe was unimaginably dense and hot, a realm where quantum effects and gravity were deeply intertwined. Traditional models of nucleosynthesis, which describe the formation of the first elements, rely on the laws of physics as we understand them today. However, these models may not fully account for the extreme conditions of the early universe, where quantum gravity would have played a dominant role. One intriguing possibility is that quantum gravity could have influenced the rate at which particles interacted during nucleosynthesis. Minute fluctuations in space-time, predicted by quantum gravity theories, might have altered the balance of reactions, potentially affecting the abundance of hydrogen, helium, and lithium. This could explain some of the discrepancies between our predictions and observations, such as the lithium problem we've discussed earlier. Additionally, quantum gravity might shed light on the structure of the early universe itself. Some theories suggest that at the smallest scales, space-time could be foamy or granular, creating a dynamic and fluctuating environment. These fluctuations could have had a cascading effect on the distribution and formation of the first elements, offering a new lens through which to view the universe's earliest chemistry. While quantum gravity remains a theoretical frontier, its potential to illuminate the creation of the first elements is undeniable. As we continue to probe the mysteries of the cosmos, the fusion of quantum mechanics and gravity could unlock answers to some of the most fundamental questions about our universe. With this in mind, let's move forward to the next theory, where we'll examine how the formation of early galaxies might have shaped the distribution of light elements across the cosmos. Now turning our gaze to the vast structures that began to take shape in the early universe, we explore the role of the first galaxies in shaping the distribution of light elements. The formation of galaxies marks a pivotal chapter in cosmic history, as these immense collections of stars, gas, and dust became the engines that drove the evolution of the universe's chemical makeup. In the early universe, the first galaxies emerged from the dense, chaotic environment left behind by the Big Bang. As matter clumped together under the influence of gravity, these infant galaxies became crucibles for the creation and distribution of elements. Within their cores, the first generation of stars, often referred to as population 3 stars, began to ignite. These stars were unlike any that exist today, composed almost entirely of hydrogen and helium, the primordial elements forged in the universe's earliest moments. As these massive stars burned brightly, they also burned quickly, ending their lives in spectacular supernova. These explosive events scattered the newly formed elements far and wide, enriching the surrounding gas clouds with heavier elements like carbon, oxygen, and nitrogen. This process, known as cosmic recycling, played a crucial role in seeding the universe with the building blocks for future stars, planets, and even life. The first galaxies also acted as gravitational anchors, drawing in surrounding gas and dust and channeling it into dense regions where new stars could form. This continuous cycle of star formation and destruction not only distributed light elements, but also created the conditions for the universe to evolve into the rich and diverse cosmos we observe today. Moreover, the feedback from these early galaxies through stellar winds, radiation, and supernova helped to regulate the growth of subsequent galaxies and the distribution of elements across vast cosmic distances. This feedback mechanism ensured that the universe did not remain a uniform sea of gas, but instead became a tapestry of regions with varying densities and chemical compositions. Understanding the role of early galaxies gives us a deeper appreciation for how the universe's first light elements were not only created, but also spread across the cosmos, setting the stage for the complexity and diversity we see today. With this in mind, we now turn our attention to another fascinating possibility: the influence of cosmic strings on the early universe's chemistry. Now, shifting our perspective to the enigmatic structures that could have shaped the cosmos in its infancy, let's explore the intriguing theory of cosmic strings and their potential influence on the formation of the universe's first light elements. Cosmic strings are hypothetical, one-dimensional defects in spacetime, thought to have formed during the early moments of the universe, possibly as a result of phase transitions as the cosmos cooled. These tiny, thread-like structures, though never directly observed, are predicted by some theoretical models, and their presence could have had profound effects on the distribution and creation of matter in the early universe. According to this speculative idea, cosmic strings could have acted as gravitational seeds, attracting and clustering matter around them. As these strings stretched across the cosmos, their immense gravitational pull might have caused surrounding gas and particles to clump together, creating regions of higher density. These dense pockets could have served as the birthplaces of the first stars and galaxies, accelerating the process of element formation. In this way, cosmic strings might have indirectly influenced the synthesis and distribution of hydrogen, helium, and other light elements by shaping the early structure of the universe. Another fascinating aspect of this theory is the possibility that cosmic strings could have generated ripples in the fabric of spacetime, producing gravitational waves. These waves, in turn, might have stirred the primordial soup of particles, altering the dynamics of element formation. While this remains a highly speculative idea, it offers a unique perspective on how the universe's first chemistry could have been shaped by forces beyond the standard processes of nucleosynthesis. Despite their theoretical nature, cosmic strings provide a compelling framework for exploring the early universe's complexities. If they existed, they could offer insights into the irregularities and patterns observed in the distribution of matter and light elements across the cosmos. While the evidence for cosmic strings remains elusive, their study continues to inspire innovative approaches to understanding the universe's origins and the forces that shaped its earliest moments. With this speculative yet captivating theory in mind, we now move to another intriguing concept that delves into the fundamental forces at play in the early universe, the role of entropy in the synthesis of light elements. Now turning to the concept of entropy and its role in the early universe, we find ourselves exploring one of the fundamental forces that shaped the creation of the first light elements. Entropy, often described as a measure of disorder or randomness in a system, played a crucial role in the dynamics of the cosmos during its infancy, as the universe expanded and cooled from its incredibly hot, dense state. The level of entropy increased, influencing how energy and matter interacted. In the early stages, the universe was in a state of near-perfect thermal equilibrium, with energy and particles distributed evenly. However, as entropy rose, this equilibrium began to break down, leading to the formation of regions with varying temperatures and densities. These fluctuations created the necessary conditions for the synthesis of the first light elements. Hydrogen and helium, the simplest and most abundant elements, began to form as atomic nuclei combined in these cooler, less energetic regions. The increasing entropy also had a profound effect on the rate of element formation. In a high-entropy environment, particles move more freely, increasing the likelihood of collisions and interactions. This facilitated the process of nucleosynthesis, allowing protons and neutrons to come together and form the nuclei of hydrogen and helium. At the same time, the growing entropy ensured that the universe continued to expand and cool, preventing the reformation of heavier elements in significant quantities. One intriguing aspect of this theory is the idea that entropy acted as a driving force behind the universe's gradual transition from simplicity to complexity. As the cosmos evolved, the increasing entropy allowed for the formation of structures like stars and galaxies, which in turn became the factories for creating heavier elements. However, in the very earliest moments, the synthesis of light elements was directly tied to the balance between energy, entropy, and the expansion of space. While the role of entropy in the early universe is well supported by theoretical models, it also raises questions about the fine-tuning of these processes. Why did the entropy levels allow for the precise conditions needed for nucleosynthesis? Was it purely a matter of chance, or are there deeper principles at work? These questions continue to challenge our understanding of the universe's origins. With the interplay of entropy and element formation in mind, we now turn our attention to another fascinating concept: the role of phase transitions in shaping the chemistry of the early universe. Now shifting our focus to the role of phase transitions, we uncover another critical factor in the formation of the universe's first light elements. Phase transitions occur when matter changes from one state to another, such as from gas to liquid or liquid to solid. In the early universe, these transitions were far more extreme, involving shifts between fundamental states of matter like quark-gluon plasma and the formation of atomic nuclei. The first significant phase transition took place as the universe cooled from its initial scorching temperature. During this period, quarks and gluons, the fundamental building blocks of protons and neutrons, began to combine to form more complex particles. This marked the transition from a quark-gluon plasma to a state where protons and neutrons could exist as stable particles. Another crucial phase transition occurred slightly later, when the temperature dropped enough for electrons to combine with protons, forming neutral hydrogen atoms. This event, known as recombination, allowed light to travel freely for the first time, creating the cosmic microwave background we observe today. These transitions were not just physical changes, but also pivotal moments that determined the abundance and distribution of the first light elements. Phase transitions also influenced the rate at which nucleosynthesis occurred. For example, the cooling of the universe during these transitions created pockets of lower energy where protons and neutrons could more easily combine to form hydrogen and helium nuclei. Without these shifts, the universe might have remained too hot and chaotic for stable elements to form. One fascinating aspect of phase transitions is their potential to create symmetry breaking, a process where the universe moves from a highly symmetrical state to a less symmetrical one. This breaking of symmetry could have introduced the necessary variations in density and temperature that allowed the first elements to form in certain regions while others remained empty. While phase transitions provide a compelling framework for understanding early element formation, they also raise intriguing questions. Why did these transitions occur at such precise moments? Were they inevitable, or did they result from specific underlying laws of physics? These mysteries continue to drive research into the universe's earliest moments. With the role of phase transitions now illuminated, we set our sights on exploring the final theory in our journey, the anthropic principle, and its connection to the abundance of light elements in the cosmos. Stepping into the realm of philosophy and cosmology, we arrive at our final theory, the anthropic principle, and its intriguing connection to the abundance of light elements in the universe. This principle suggests that the conditions we observe in the cosmos, including the distribution of hydrogen, helium, and lithium, are not random but rather finely tuned to allow for the existence of life. In other words, if the universe had not formed these elements in the precise way it did, life as we know it might not have been possible. The anthropic principle comes in two main forms, weak and strong. The weak anthropic principle simply states that we observe the universe to be the way it is because we exist within it. If the universe had different properties, we wouldn't be here to observe it. This idea applies to the abundance of light elements in an interesting way. For instance, if hydrogen were less abundant, stars might not have formed in the same way, and complex chemistry, essential for life, might never have emerged. The strong anthropic principle takes this a step further, proposing that the universe must have properties that allow life to develop. This version of the principle often leads to speculative discussions about the nature of reality itself. Could the universe have been designed or fine-tuned to support life? While this idea ventures into philosophical territory, it raises fascinating questions about the relationship between the cosmos and life. One way to think about this is through the lens of the early universe. The precise conditions during nucleosynthesis, the temperature, density, and rate of expansion had to be just right to produce the correct proportions of hydrogen, helium, and lithium. Even slight variations in these conditions could have resulted in a universe with vastly different elemental abundances, potentially making it inhospitable to life. Critics of the anthropic principle argue that it is not a scientific theory but rather a philosophical observation. After all, it doesn't explain why the universe has the properties it does. It simply acknowledges that we observe it because we exist within it. However, this principle has inspired researchers to explore the fine-tuning problem, asking whether the laws of physics and the initial conditions of the universe are uniquely suited for life, or if there are other possible explanations. As we conclude our exploration of the universe's first light elements, the anthropic principle leaves us with a profound thought. The abundance of hydrogen, helium, and lithium isn't just a matter of cosmic chemistry, it's also a reflection of the delicate balance that makes life possible. Whether you view this as a scientific insight, a philosophical observation, or a mystery yet to be solved, it's a reminder of how deeply interconnected the cosmos and life truly are. And with that, we've journeyed through 30 fascinating theories about the universe's first light elements, each offering a unique perspective on the origins of everything around us. What do you think about the anthropic principle? Do you believe the universe was fine-tuned for life, or is it all a cosmic coincidence? Share your thoughts in the comments below, and don't forget to subscribe for more deep dives into the mysteries of space. With our journey through these 30 theories now complete, one thing is clear. The universe's first light elements are far more than just the building blocks of matter. They are the foundation of cosmic mystery and wonder. From the primordial nucleosynthesis that sparked hydrogen and helium, to the speculative role of dark matter and exotic particles, each theory offers a unique lens through which we can glimpse the origins of everything around us. We've explored how quantum fluctuations, cosmic inflation, and even the enigmatic properties of neutrinos might have shaped the early universe. We've delved into the mysteries of the lithium problem, the abundance of helium, and the influence of cosmic rays. And we've pondered the profound implications of the anthropic principle, raising questions about whether the universe was fine-tuned for life or if it's all a remarkable coincidence. What ties these theories together is the sheer complexity of the cosmos and the unanswered questions that continue to inspire scientists and thinkers alike. The universe's first light elements are not just remnants of the Big Bang, they are clues to understanding the very fabric of reality itself. As we wrap up this exploration, I want to hear from you. Which of these theories do you find most compelling? Do you have your own ideas about how the first elements came to be? Share your thoughts in the comments below. Your perspective might just spark the next great cosmic discussion. And if you've enjoyed this deep dive into the mysteries of the universe, don't forget to subscribe and hit the notification bell. There's so much more to uncover, from the secrets of black holes to the enigmas of dark energy. Together, let's keep exploring the wonders of space, one theory at a time. Thanks for watching, and until next time, keep looking up.